The next display dimension we'll talk about is information type. Information type has also been called data type in other places, and I'm sure it's called other things as well. But basically what we're trying to get at here is that for the data that you're trying to display, you can either display that as continuous or categorical. Now sometimes what you're given is not continuous, so it's going to be categorical, but oftentimes you'll get continuous data and you'll be tempted to make it categorical. And we want to go through and explicitly start thinking about and talking about why you would or wouldn't do that. So when we're thinking about continuous, these are things that are measured out in the world. Some examples of that are waist size or shoulder width or height or weight or etc. These can be compared. Continuous data is often of the data type ratio, which means 5 is 5 times 1, 10 is 2 times 5. It is, if I have a 10 if I've measured 10, that's 2 times if I would have measured 5. And that way these can be compared directly. And what we really are, the benefit of the continuous is we can accommodate intermediate states and trends. So there is such a thing as a 7.5. There's an 8 3/4. Those things exist in continuous. So we haven't made those discrete. Once we make them discrete, then we're talking about categorical data. The best example I have is t-shirt sizes, so small, medium, and large. So there are all kinds of different people, all kinds of different sizes, but most t-shirt companies are making small, medium, and large. So if you happen to be a medium and a half, well, you get to be a medium or you get to be a large. And when we're thinking about our data and how we're going to describe our data, we would do this because the categorical is oftentimes more compact and it suppresses unnecessary details. So if you don't care that it's, this is oftentimes done with population distributions or age distributions, that we don't necessarily care that somebody's 37 and a half years old. We care that they're between 32 and 40, or we care that they're between 25 and 35. So if you're in that category, where you fit within that range, what we would call this intermediate state, has been determined to be unimportant. And oftentimes these are well suited to rule-based decision support systems, like good-bad dichotomies. It's also well suited for those places where the categories are non-overlapping and really do adequately describe the differences between different parts of your data. So as I said before, categorical data is nice and compact. You can actually compress quite a bit of data, continuous or otherwise. You can compress quite a bit of that into just a few different data elements, and sometimes that's absolutely necessary. I think I want to show you how it's necessary and how it can distort your information or the information that's gleaned from it. This is a good example of that. So what you're looking at here is for one health system. There's a study done on one health system, and this was the annual inpatient CT imaging volumes and rates for the abdomen and pelvis, head, sinus, and lumbar spine from 2008 to 2012. So if you look at this, these are actually the volumes and rates. So this is volumes. This is total number of CTs. So for 2008, there was about 4,200 CTs performed at this one health system. And so, if you think about that, that's 4,000 divided by 365. So there's, an average of 10 a day, a little bit more than 10 a day. So if we wanted to describe each one of those, per day, that would be a graph in and of itself, and it would be a really large graph. So if I wanted to compare years, that's very difficult, if I were to take this completely as continuous. So we need to group them, and grouping is a categorization, and so as we group them into years to do this. And so we have, all of them for 2008, 2009, and this is pretty common. Years is that's a pretty typical container when I'm thinking about time. So are months and days, but let's, focusing in on years here. So the issue with categorization is that for there to be category, there needs to be a window or a categorization method, and that window or that categorization method makes explicit or implicit assumptions of what are important boundaries. So for this one, it makes it an implicit assumption that even if it's December 31st, 2008, that's different than January 1st, 2009, or that that it doesn't distort the data by keeping those far apart. So even though December 31st, 2008 is probably more dissimilar to January 1st of 2008, they're all lumped together in here, these are all lumped together in here. So you're making this implicit assumption at least that that's an important boundary. So one of our big findings was that if you look through here, that overall it raised up through 2010 and then came back down through 2012, and that was a pretty interesting finding. However, you can see if you look through this is a stacking bar chart, you can see that most to all of that difference is actually coming through abdomen and pelvis. And so there's a little bit of a rise and then a pretty gradual but substantial decrease through 2012. So again, we're pretty excited about that. So again, we're making implicit assumptions that the year markers are very important boundaries. We're also making an implicit assumption that there aren't other important boundaries or confounding boundaries. And that was actually not a good assumption in this case. What we found out after putting this graph together was that there was actually a reporting difference that came through insurance. Insurance expected these things, especially abdomen and pelvis, to be reported differently, and they actually reported all abdomen and pelvis as one exam in 2011, starting in 2011, whereas 2 exams in 2010. And most times these are done together. So this happened actually, and because it happened in 2011, but happened in July 1st, because that's where the breaking point or the fiscal year hit. We didn't get a huge difference here, and you finally get the full extent of that in 2012. And if you look at the data, this is just about half of this, and this is about 3/4, which would make sense because for 6 months it would only be reporting half basically. So that was a much better boundary, and if once we switch this to fiscal year, you would see a huge drop off, and it stayed relatively the same. So in this case, the categorical distorted the data, although it made a very pretty graph. It was completely distorted, and if we were to make a series of inferences based off these data, we would be misinterpreting, and we could be leading ourselves to wildly incorrect inferences. So now let's look at the Tableau challenge that you just completed and look at maybe not wildly incorrect inferences, but how in categorizing the data it made it difficult to see certain things. So what we're looking at here are relative obesity levels across the United States, basically by state, for the year 2012. And if we were to make decisions, if we were decision makers on this, we're looking at which states would we go after. It's pretty clear that we definitely have obesity problems here in the Mississippi River Delta, and then up the Mississippi River. Those states, although I don't know if that's the cause, but this kind of area of the kind of western South seems like West Virginia is problematic, and there are others that there maybe as you go up north here through here, up through here also could be problematic. But in general, these are the big red ones. And in general, you can also see that wow, this is pretty easy to see this map when I categorize by state like this. It's pretty easy to see which are the states that have the most problems and the least problems. So now let's compare this with 2010 data, which is going to be slightly different, because 2 years had occurred, but it's not going to be, the obesity number shouldn't change that much. But what the big change that happened was that these data were reported by county in 2010, they were reported by state in 2012. So now you're looking at the data in 2010, and in general, most of the areas look pretty much the same. California was pretty green in the last map, and most of the counties are pretty green in this map. Same thing throughout the West. Not many huge obesity issues here. I want to draw your attention to 2 different areas, though. First, this area up here, and then this area down here. First, let's go through this one. So this is smack dab in the middle of South Dakota and North Dakota. Let's zoom in here. And so I want you to think back. Did you think that South Dakota or North Dakota were particularly notable with their obesity levels in 2012? If you didn't, you would not be alone. They were basically the kind of yellowish color. They weren't. In fact, they were kind of tending towards the green. These seem like pretty decent states. But these counties within there, so just so you can feel for a little bit of reference, right here is the North Dakota, South Dakota border. And then here's the bottom border of that state of South Dakota, and I think it goes down through here, but don't quote me on that, since I think it's about there. Yeah, that's about right. So you can then see the little, actually, yeah, it is right. So you can see the South Dakota watermark in there. And so there's something going on with these counties, and it didn't show up on the state map at all. With just a little bit of Googling, it's pretty clear that all of these are a series of Native American reservations. And it actually, as these borders are very distinct. These counties contain reservations. These counties do not. This county does not. This county does. In fact, it is in its entirety. All of these are in their entirety reservations. And so this would lead to a very different picture of how would we fight obesity in America, and where should we be going after first. Now, it's not to say that we only go after Native American reservations, but these data just didn't show up at all. So now let me zoom out a little bit. And let's see, what are some other issues or areas? The other thing that I can see pretty quickly is this area through here. And then with just a little bit more work, I can start to see, that one is maybe the most red. There's also some red counties through here in Alabama. But there seems to be some kind of trend going on up here, and then if I can kind of follow that around, if I just look at just the difference between counties relative as neighbors, I can see this trend in some ways continues all the way up here and then all the way up to there. Now it's not as red, but the surrounding counties are not as red either. So as a difference between counties, that seems to be somewhat of a trend, or we should probably look at that further. And for those geography buffs, this is the Ohio River coming down through here and connecting up with the Mississippi River. So there definitely could be differences and disparities, on these riverside towns. I know that as an Ohioan, I know that they like to call this the Rust Belt, and up into here is the Rust Belt. I don't like that a whole lot, but it seems to have taken on. And so a lot of these river towns were booming at one point, and they're no longer booming. We have differences in how we ship goods and things like that. And so once you kind of put that in perspective, you may be able to see a whole lot more of these. But all of these differences, all of these more detailed things that could be seen at the county level get obscured if you think about it at the state level. So I hope that these examples can show or do show that as you're creating your designs, as you're trying to think about how you're going to display your data, you explicitly think about the boundaries that you're putting in the world, or the boundaries that you're using as your categorization, and are those boundaries relevant, or are there other confounding factors that would cause you to think about different boundaries, or more granular categories, less coarse categories. And in that way, you can start to make the trade-off between more categorized data and more continuous data.